Hello everyone, welcome to the next video. In this video, we are going to discuss how to build the block diagram for our FFT accelerator. So as usual, we will start with the Vivado. So we'll start with the create project. So in the create project, we'll go to the next in the lab 3, I'll say demo, then next. So here I'll include the board, which is our zedboard from Digiland. And click on finish. Okay, so then we will create our block diagram. So click on create block diagram. So after creating the block diagram, first step is to add the Zynq IP. So we will find out the Zynq IP in the IP catalog and select that Zynq IP. So after adding the Zynq IP, first run configuration with the default setting. Then include the setting as per our requirement. So as per our requirement, we will be using the ACP port as discussed in the previous video. Okay. Other than that, we don't need the TTC counters and some of the interface. So we'll go to the peripheral. We will remove this in peripherals. We'll only keep the UART for debugging purpose. Okay, so we will need a PL fabric block because we are using the FPGA in this lab. So ARM operate at 666 megahertz. Yeah, so this looks fine. Click OK. Okay, so you can see that the ACP port has been added so that FPGA can use this ACP port to communicate with the Zynq along with this GP port. As I told you before, GP port is a low-speed peripheral. It is used for the configuration, while the ACP port can be used for the data transfer. So the next thing we need to add is the DMA. So we will add the DMA. So there are multiple DMAs are there. Right now we will use the direct memory access. The rest of the DMA we will discuss in the lecture. So this is the DMA. Before doing the connection automation, first we will configure the IP as per our requirement. So in the DMA or any other IP you use, you should click on the corresponding documentation, or on the online you should select you should search for the Xilinx AXI DMA 7.1 and you will get the corresponding document. And in that document, all the details about this are mentioned. For example, in this case, we don't need a scatter gather. What is meant by scatter gather, we will discuss in the lecture. But in the simple DMA, what we are going to do for every transfer, we are going to configure the DMA. In the scatter gather one, you can configure the DMA to do the multiple blocks of transfer. Okay, in one go. So you only by using one configuration, DMA can transfer multiple blocks of transfer from multiple source to the multiple destination. But in the simple DMA mode, you can transfer only one block of transfer from one source to the one destination by one configuration. So we are using the normal mode, simple mode. These settings, you just keep it as it is, don't need to worry. Now, DMA will be doing the read operation as well as write operation. So we need to configure it. So for example, if you see on the DMA, there is this AXI light port, and as you know, AXI light port is used to configure the DMA from any master. So how should DMA work in the real time, you can configure. So suppose you want to enable the DMA to do the simple transfer. So you can tell the DMA via AXI light port what are the source, what is the destination, and how much data to be transferred. Similarly, you need to know whether the DMA transfer is complete or not. So you can again use the AXI light to read the particular register in the DMA, and by looking at that register, you can see what is the current status of the DMA. So we will understand this more in detail when we'll write the C code. Now here you can see that there are 4 ports. Out of 4 ports, 2 are the AXIS, that is the stream port, and here is another stream port, and then there are 2 memory mapped AXI port. Now, as we know that the DMA will receive the data from the memory, that is via memory map port, and it will pass to our FFT, that is having the stream port. So the memory map to stream conversion is taken care by the DMA. Okay. So in our case, we are doing the FFT, and our inputs are the complex number. So what we need to do, we need to make sure that every data bus is 64 bits. So even for the stream, so this data bus corresponds to the memory map bit, that is these ports which are connected to the memory. And then for our FFT also, we will make it 64. And the bus size right now we will make it 256, but it is good to choose it as per our application requirement. But right now, just make it as 250. We can click the allow unaligned transfer for now. Now we will discuss more about it in the future lab. Now, similarly, read channel, write channel. Again, here we need to make it as a 64 one. This one right now we are not able to make it, but once we complete the block diagram, tool will understand that our data width is 64 bit even from the FFT output. So it will change it to 64 bit. And this is again 256, and you should click on this one. Okay, so that's it. So what here we are telling the DMA that you should perform the simple transfer. In the simple transfer, your data width is 64 bit, and your maximum burst size or burst length can be 256. Now, if you see here, to S, here you can see that your data width has become 64 bit. Okay, that is what we have changed it. Here also, you can see that data width right now it is AW data. Data is 64 bit. So the memory mapped one, both have been 64 bit. Now this one, you can see that the S to MM, that is the stream data width, is still 32 bit. But after once we do the connection with the IP, it will be changed to 64. And this one, MM to S, it is 64 bit. That is this one. Okay. So this is very simple to configure the DMA. So we have configured the DMA. Click on OK. Okay. So now we need to understand where to connect which port. Now this AXI light port, we know that it will be configured by the processor via GP port. So we need to connect this AXI light port to the GP port. That is quite clear. Now these 2 ports, we need to connect it to the ACP port. Now you can see that for the ACP port, there are 2 masters. From the DMA will be the master to the ACP port. So we need to have the AXI interconnect. Again, we don't need to do it manually. You can use the run connection automation. Then we can see that we will select the AXI light. AXI light, you can see the tool will tell, okay, connect it to the GP0. So tool is smart enough to do that. And then for the ACP port, here you can say that the tool will say that connected to the memory map to stream. So that is what the tool is doing. So let's click on OK. So now if you want to redraw the diagram or regenerate the layout, you can click on this button. Okay, so here you can see that what we have done. This is your Zynq IP. Zynq IP GP port, you can see, is connected to the AXI light port via AXI interconnect. So this is the interconnect is added so that you can connect the multiple masters, multiple slave. Then the to AS port is connected to the ACB port via again the smart interconnect. But we also need to connect the S to MM. So tool has also identified that. So we run correction automation. So S to MM again to the ACP port. So you can see that it will connect the ACP port. So you can see that there is a one master slave has been added here and then the same master. You can do it manually also. You can click on this and add the slave and master interface. You can do it manually, but here the tool is taking care of this one. So now you can see that this DMA can be configured by the processor by AXI light port, and this DMA can read the data from the ACP port, that is on-chip memory of the Zynq SoC, from the ACP port via this S2MM and the M2SS memory map port. Now the DMA has read the data. DMA has to pass the data to the IP. So we will use the FFT IP as our example. So FFT is our IP. So click on the fast Fourier transform IP. Again, for the FFT IP, the details will be there in the corresponding document. For every IP, Xilinx has provided the detailed document, how to configure the IP, how that IP works, what are the features supported in the IP. Everything is there. So this is my IP. So this is the IP. Again, in the FFT, I'm going to do the 8-point FFT. So I'll select the 8-point FFT, that is the transform length. Rest of the things, I won't change anything. Then in this implementation, my input is coming as a floating point. So what I'm going to do, I'm changing it to the floating point because my input is floating point 1. Rest of the things you will keep it as it is. I want a active low reset because in the entire AXI, all the reset are active low. So I'll also use the active low reset in case I want to reset the FFT IP. Okay. I want my output to be in the natural order as we are doing even in our C code. Inputs are in the as per the desired order, but the outputs are in the natural order. So that's why I'm making the output should be in the natural order. And that's it. Rest of the things we don't need to change. Again, if you want to know more, type Google search for the document Xilinx fast Fourier transform 9.1. You will get the corresponding IP details. Now in the implementation details, you can see that how the channels are there. All the information is there. You can know more about this information. For example, this IP can be used as a FFT IP as well as IFFT IP. So you can see that in the configuration one, if you on the 0th base address, if you make the last bit as equal to 1, it will work as a FFT, otherwise it will work as a IFFT IP. Similarly, you can control the scaling and all those things. Again, all this information you will know once you read this document. So click OK. So now here you can see that the tool is not able to identify where to connect the IP. And in this case now, your knowledge will help us to connect it, the IP properly. So we know that the output of the DMA on the AXI one should be passed as an input to the IP. So you will select this port and you will see that here you can connect it to the both the configuration and data, because tool doesn't know where to connect it. Tool only know that the input port is a stream port. So the output port should also be stream port. But we know that it should be connected to your data port. So then you connect to the data port. Now, output of this IP, you should connect it to the input of the DMA. So you can see that the slave port of the DMA, Okay, and you can see that you can connect it here. So you will get the green color tick, so indicating that both the ports are compatible. Now the configuration port. Now this configuration port is also stream port. So for now, what we'll do, we will connect the constant value to the T data and the T valid signal, indicating that we want to perform the FFT. So what we will do, we will take the constant one, because the processor cannot communicate via the AXI stream interface. So we need to either you design our own IP, which will do the configuration for the FFT. But right now, to keep the lab simple, we will just connect the constant one. So data is 1, it is 8-bit data, but the value is 1, indicating that we want to perform the FFT operation. And we also copy this one more time to make the valid is equal to 1, because for the IP you need a data as well as valid signal. So we will keep this valid signal as a 1-bit valid signal. Okay, so you can see that here I am connecting the valid is equal to 1. Okay, so that the IP knows what operation you need to perform, FFT or the IFFT, via this interface. Now you can see that the again tool is not able to connect the clock and reset, so we need to make sure that we connect the clock and reset. So you can see that I'm connecting the clock to the same clock where every IP is connected. Then I'm connecting to the reset to the same reset to every IP is connected, and that's why you need to make sure that your reset is active low. If you make the reset as active high, then your IP, when the rest of the IPs are working, your IP will be in the reset mode and you won't get the output. So that's why understanding these designs is very important. So this completes our main logic, where we have connected the we connected the DMA and FFT to our Zynq processor via AXI interconnect. Now, from the Zynq processor point of view, you can see that from the Zynq processor or ARM processor, it can only see the DMA. It cannot see the FFT IP, because FFT IP is a stream IP which is inside the FPGA. It doesn't have any address, right? Because stream interface doesn't have any address. So from the Zynq one, it is communicating only to the DMA. DMA is communicating to the FFT, but for the Zynq one, it is there is no idea what kind of FFT IP is there, because there is no address. It is not memory map. It is a stream interface. So even in the address editor, you will see that there is no Zynq IP. The FFT IP is there because processor cannot see the FFT IP. Processor can see only up to the DMA IP. That is only the IP which has the memory map, which has some address. Okay. Now, for the debugging purpose, we want to know how this data are being communicated, how this data are being passed from one IP to IP. So we can add the logic analyzer, which will be able to help us to visualize this data. So what I'm going to do, I'm going to add the inform the tool that I want to analyze these pins while doing the simulation. So what I need to do, I need to select whatever the interface I want to select and mark as a debug. So here I have marked this as a debug, which is the FFT output. Then FFT input is also I have marked as a debug. Okay. Then I have marked the debug as a DMA input from the processor, or from the memory, and the DMA output to the memory I have also marked as a debug. And then how the DMA is being configured, I also mark as a debug, so that I'll be able to understand all this signal. And then run connection automation tool knows that I need to add the corresponding the ILA here, that is the logic analyzer. So this logic analyzer is the integrated logic analyzer. So what it does, when we are running our code on the board, it will capture the data when the corresponding trigger condition is set, and it will pass it to the debugger, so that our tool will be able to display the data. So when our code is running on the board, the on-chip data is being captured and it will be displayed on this Vivado tool. So that's why we will see what is actually happening inside our chip via this integrated logic analyzer. Okay, so this is the logic analyzer. Again, you can see that this block is also Verilog, written in Verilog, and it will be taking some space on your FPGA. But for debugging purpose, it is usually what is done during the debugging phase. It is added, and once your product is finalized, this block is removed so that your resource utilization or power consumption can be reduced. Okay. So in this block, there are some settings are there. Again, if you want to know more about this block, you can look at the corresponding thing. You can see that it also mentioned how much resources are used, because on-chip memory is required to capture the data. And you can see that the interface are your whether it's the AXI interface or the normal interface, you can mention those things. Again, in the future lab, we will discuss more about this one. What is I want to show you is the depth, like how once your trigger condition is met, how many samples you want to capture. Okay, so here you can see that 1024 you can go up to the large value. Suppose I went to 2048, you will see that your memory utilization will increase on the left. You can see. So you need to choose it carefully, how much you want to capture. So right now we will keep it as a 1024. Okay, all this capture control, trigger control, we will take some time to understand all these things in our subsequent lab. Right now we want to keep it as simple as possible. Okay, so this completes our block diagram. Once the block diagram is complete, once your addresses are correct, okay, so first thing is to validate your design, because that is what we do. After validation of your design, you need to generate the output products, then create the HDL wrapper, and then you need to generate the bitstream. So this time we need to generate the bitstream because we are going to use the FPGA. So we need to generate the bitstream and use that bitstream for the FPGA configuration. Okay, so the validation is successful, so that's good. So after the validation is successful, I would like to show that DMA interface. You can see that this has been changed to 64 automatically, because now the tool knows that this is connected to your FFT IP, which has a 64-bit interface. Now let's go to our block diagram. In the sources block diagram, right click, generate output products. Okay, so this generate block design, generate output products will take some time. Okay, so you need to make sure that you can click on background, and you need to make sure that you go to the next step only after you get the ready in the top right corner. Once you get the ready here, then the next step will be the generate the create HDL wrapper, and then you click here on the generate bitstream and the left bottom. Okay, so before during that time, I would like to show you the two documents for the IP which we are using. For example, one we are using is the DMA IP. So you can see that for the DMA IP which we are using, the corresponding document is already available online. And in this document, entire things about the DMA is given, how to make use of the IP, what are the features are there, and everything is mentioned in that the IP. So I don't recommend you to go through it now, because it will be too much for you to understand it. But some of the details which I'm going to use it, I'll show you here. For example, these are the interface we have been using, right? In the DMA, there is a one AXI interface to configure the DMA. So if you go here, you can see that this is the AXI interface, which is used to know the configure the DMA, that is to access the register inside the DMA, or to know the status of the DMA. Then you can see that there is a AXI memory map read and the AXI memory map write, which we connected to the ACP port. Then there is a memory map to stream and the stream to memory map, which is connected to the your FFT IP. Okay, so this is completed, but it's still it's still output products are still generated. So then the important thing is the register space. So you need to know how to configure the DMA, how to read the current state of the DMA. So you can see that from the base address, you can see that there are different registers are there. For example, you can see that this is the control register and the status register of the DMA for the M2SS. So in this case, you can see that from the control register, you can control the DMA. You can tell the DMA what to do. And from the status register, you will know what is the current status of the DMA. MM2AS is memory map to stream. That is when you want to send the data from your memory to your device. Then you will use this register. When you want to read the data from your device to and send it to the memory, you will use S2MM, and you will see that the same control and the status. So in our C code, you will see that we will using this 34 and the 04 register to read the status of the DMA, and we'll use the 0 and the 30 to control the to configure the DMA. Okay, this is how we will use. And then right now we are not using this description pointer because these are used for scatter gather mode. But for us, these two registers 0, 30, 34 and 04 are important because from this we will know the status of the DMA and we will be able to control the DMA. Okay, so this is what. So this was the scatter gather mode, but you can see that we are using the simple mode, that is this mode where these registers are being used. Then in our simple mode, we also need to tell from where the data should be taken from the memory. So we need to provide the source address. So we can provide the source address on the by writing into the particular register. We need to tell the destination address. So we need to tell the destination address by writing into the particular register. Then we need to tell how much data to be transferred. So we can send the transfer length by using this writing into this register. So all these registers are there, which we need to make sure that we need to make use of them carefully. Okay. Same case for the FFT IP. You see that there is a FFT IP. All the details about the FFT IP is given. Okay, how this FFT IP work, what are the equations are being done, what are the configurations are need to be done, what is the type of the reset. So you can see that if you want to do the forward one, you need to make that corresponding bit is equal to 1. Forward means FFT operation, backward means IFFT operation. So in that case, you need to, as we did done in the our block diagram, we have made the corresponding LSB bit as 1. So that's what this information we got it from this one. Okay, so you can see the configuration data channel, and you can get the in the FFT, the IP is that you can also configure this FFT, how many point you need to do. For example, for one bunch of data, you need to do 8 point FFT. Then you want to do the 16 point FFT. That is also configured it. For that, you need to make sure that you enable the runtime configuration in your FFT IP. I'll show you how to do it. Now, in the wireless communication, in the OFDM, you also need to do the CP addition. So that cyclic prefix addition. So that feature is also incorporated here. Then here you can see that whether you want to do the forward FFT or you need to do the inverse FFT. So that corresponding bit is there. Okay. So all this information is there. You can see that this bit is in the LSB, that NFFT bit. So that's why we are checking the LSB bit. Okay. That is the one we are doing it. So yeah, so this is the one. Okay, and sometimes depending upon the how you configure the IP, you also need to look at the implementation details. For example, here it is clearly saying that the bit 0 is corresponds to the whether you want to decide the forward or inverse, because we have chosen the FFT size to be fixed to 8 here, but in the document, if you look at there is a slight change in this one. So it is always depend upon how you configure the IP. You should refer to the implementation details to get the more understanding about the how to set up the corresponding IP. Okay, so after your this one output generate output product is done, right click here and create HDL wrapper. Okay, so after creating the HTML wrapper, the last step is to generate the bitstream. It will take around 4 to 5 minutes. Okay, so my bitstream has been generated. I'll click on cancel, and then I'll export the hardware, but in this time I'll include the bitstream. And the next step is to launch the SDK so that we can write our C code or the application code for the ARM processor.